Alright, finishing up this series of videos, last one, examining the physics of Professor Walter Lewin at MIT and such. So, without further waste of time, yeah, let's do it if we can evade the commercials.
Today I want to talk with you about Doppler effect, and I will start with the Doppler effect of sound, which many of you perhaps remember from your high school physics. If a source of sound moves towards you, or if you move towards a source of sound, you hear an increase in the pitch. And if you move away from each other, you hear a decrease of a pitch. Let this be the transmitter of sound, and this is the receiver of sound. Could be you, your ears. And suppose this is the velocity of the transmitter, and this is the velocity of the receiver.
Let's see, do I have anything to say? Yeah, so it really doesn't matter for most redshift circumstances. What the receiver and the emitter are doing is reciprocal in a way. And the only thing that really matters is that when the thing is put into the environment, it does its own thing. So even at the speed of sound, or that can be variable depending on the density of the material, the sound itself does its thing. You can't make it go faster or slower. The speed of sound is the speed of sound. So in that sense, electromagnetic radiation and sound have that in common, in the sense that you can't make the sound go faster or make the sound go slower. So all you're changing is frequency. If something's moving towards you, then it's going to drop the sound in shorter increments of distance. And if it's moving away from you, then the sound it's dropping, okay, is going to have a longer distance between when it gets dropped. Like if you were dropping paint out of the trunk of a moving car, the distance, you would say, I'm doing it every 10 feet, but it's not going to be 10 feet because you're moving, kind of thing, mostly.
And v should be larger than 0 if the velocity is in this direction, and in the equations what follow, smaller than 0 it is in this direction. The frequency that the receiver will experience, will hear, if you like that word, that frequency I call f prime, and f is the frequency as it is transmitted by the transmitter. And that f prime is f times the speed of sound minus v receiver divided by the speed of sound minus v of the transmitter. So this is known as a Doppler shift equation. If you have volume 1 of John Coley, you can look it up there as well. Suppose you...
Again, it's just the frequency that gets changed. So no velocity is changed in the process. So no velocity changes, just the frequency of how often the thing that is moving is dumped. So if you think of it as a wave compression, just has to do with the distance between the compressions. If you're moving towards something, the distance between the compressions will be shorter. You're moving away, the distance will be longer.
You are not moving at all, you're sitting still, so v receiver is 0. But I move towards you with 1 meter per second. If I move towards you, then f prime will be larger than f. If I move away from you with 1 meter per second, then f prime will be smaller than f. The speed of sound is 340 meters per second. So if f, which is the frequency that I will produce, is 4,000 hertz, then if I move to you with 1 meter per second, which I'm going to try to do, then the frequency that you will experience is about 4,012 hertz. It's up by 0.3%, which is that ratio 1 divided by 340. And if I move away from you with 1 meter per second, then the frequency that you will hear is about 12 hertz lower. So you hear a lower pitch, about 0.3% lower.
Oh, 0.03%, I think. I mean, frankly, 12 is a very small percentage of 4,000. So something's wrong with that, but it doesn't matter.
I have here a tuning fork. Tuning fork is 4,000 hertz. I will bang it, and I will try to move my hand towards you.
I guess where he gets the 0.3 from. 0.3 would be 1 in 100, and then it's 1 in 1,000. So 12 out of 4,000 would be 4,000 into 12 would be 3. So okay, that's where you get the 0.3 from.
1 meter per second, roughly. That's what I calculated it roughly is. Move it away from you, towards you, away from you. As long as the sound lasts, you will hear the pitch change from 4,012 to 3,988. Very noticeable. You heard it? Who has heard clearly the Doppler shift? Raise your hands, please. Okay.
Not exactly a meter, but whatever.
Very clear. Increase frequency, and then when I move my hands away, a lower pitch. Now you may think that it makes no difference whether I move towards you or whether you move towards me.
And it doesn't. So I think he's just wrong here. I did ask him in a comment section if he had any evidence, like if there was any experiment he could point to where they demonstrate that it makes a difference. And he told me Sputnik. Sputnik is electromagnetic waves. It's a sound tone on light waves, that kind of thing. So, not an example.
And that is indeed true if the speeds are very small compared to the speed of sound. But it is not true anymore when we approach the speed of sound.
So again, it's not true any time. You can't. Just doesn't matter. Emitter, receiver moving, it just doesn't matter in all circumstances.
As an example, if you move away from me with the speed of sound, you will never hear me.
Just catch 22. If I move away from you at the speed of light, you'll never see me. So, just because we've stated you can't go the speed of light, well, I'm just saying if I could, then no light would ever catch me. Even if it was 2 feet away, I'd still be ahead of it. Just a fact. So what?
Because the sound will never catch up with you. And so f prime is 0. And you can indeed confirm that with this equation.
And again, I got to confirm it relativistically also by just pointing out that as a thought experiment, if I did go the speed of light, you couldn't catch up to me.
I moved away from you with the speed of sound. For sure the sound will reach you. And the frequency that you will hear is only half of the one that I produce. So there's a huge asymmetry.
There's no asymmetry. There just isn't any. Like I said, you can do the same thought experiments as with the speed of light. The same is true for the speed of light. If I move away from you at the speed of light, I'm still going to receive. I mean, if the receiver moves towards me at the speed of light, it'll still be the same truth as it's half the speed of light, or half the speed of the sound. If it's sound, so it doesn't make any difference.
Big difference whether I move or whether you move.
So he says big difference, huge difference. No, there's no difference. I could find any evidence of a difference ever being demonstrated anywhere. So there's no difference.
So I now want to turn towards electromagnetic radiation. There is also Doppler shift in electromagnetic radiation. If you see a traffic light red, and you approach it with high enough speed, you will experience a higher frequency, and then you will see the wavelengths shorter than red, and you may even think it's green. You may even go through that traffic light.
Yes, we're talking about going like a quarter of the speed of light or something, some kind of preposterous amount of speed. Probably faster than that with the Lorentz transformation. You probably have to go 80% or something.
Calculate the proper relation between f prime and f requires special relativity. And so I will give you the final result. F prime is the one that you receive. F is the one that is emitted by the transmitter. And we get here then 1 minus beta divided by 1 plus beta to the power 1/2. Beta is v over c, c being the speed of light, and v being the speed the relative speed between the transmitter.
So they're just doing this plus minus the speed of light mush. That's their Lorenzi, don't allow anything to go to the speed of light kind of thing.
And u. If beta is larger than 0, you are receiving from each other in this equation. If beta is smaller than 0, you are approaching each other.
And again, see, they want to keep forcing everything to be some sort of, it doesn't matter who's moving thing. And it does matter. There's a truth. One thing has a difference in its energy, or velocity, and one thing doesn't. It's not towards each other or away from each other. One thing is likely, in most cases, creating any shift that exists.
You may wonder why we don't make a distinction now between the transmitter on the one hand, the velocity, and the receiver on the other hand. There's only one beta. Well, that is typical for special relativity. What counts is only relative motion. There is no such thing as absolute motion.
So again, another statement that just, sure, there's absolutely no evidence that there's no such thing as absolute motion, because in all the circumstances I can sort of point out an absolute motion. If you put windows on everything will see the absolute motion. Unless you want to believe that, say you're in a spaceship and the universe is flying by very, very fast. I mean, you could have the silly assumption that you're standing still and the universe is moving away from you, but that would be kind of retarded.
The question, are you moving relative to me or I relative to you, is an illegal question in special relativity. What counts is only relative motion.
Well, it doesn't count in terms of the fact that if you understand that velocity has an effect on your metabolism, that when you have velocity, you actually have captured velocity. That means you actually have an orientation of your molecular structure that keeps your velocity. It does matter.
If we are in vacuum, then lambda equals c divided by f, and so lambda prime equals c divided by f prime. Lambda prime is now the wavelength that you receive, and lambda is the wavelength that was emitted by the source. So I can substitute in here, in this f, c divided by lambda, which is more commonly done. So this Doppler shift equation for electromagnetic radiation is more common given in terms of lambda. But of course the two are identical.
I'm not quite sure what happens to this equation in the circumstance where two things actually do move away from each other at, say, 90% of the speed of light. Then the Doppler shift would end up being larger than the speed of light. Yeah.
And then you get now 1 plus beta upstairs divided by 1 minus beta to the power 1/2. The velocity there, if I'm completely honest with you, is the radial velocity. If you are here, and here is the source of emission, and if the relative velocity between the two of you were this, then it is this component, this angle is theta, this component which is v cosine theta, which we call the radial velocity, that is really the velocity which is in that equation. Police cars measure your speed with radar. They reflect the radar of your car, and they measure the change in frequency as the radar is reflected. That gives a Doppler shift because of your speed, and that's the way they determine the speed of your car to a very high degree of accuracy. You can imagine that in astronomy, Doppler shift plays a key role because we can measure the radial velocities of stars relative.
Yes, it's always relative to the thing that could already be moving. Yes.
To us. Most stellar spectra show discrete frequencies, discrete wavelengths, which result from atoms and molecules in the atmosphere of the stars. Last lecture I showed you with your own gratings a neon light source, and I convinced you that there were discrete frequencies and discrete wavelengths emitted by the neon. if a particular discrete wavelength, for instance, in our own laboratory, would be 5,000 angstrom.
So let's understand that these signatures require very many photons for you to receive. So it's not information that's on one photon. You have to receive enough information to see the spectral lines, which means you have to collect a lot of photons to be able to recognize these lines.
I look at the star, and I see that that wavelength is longer, lambda prime is larger than lambda. Then I conclude lambda prime is larger than lambda. That means the wavelength, the way I observe it, is shifted towards longer wavelength, is shifted in the direction of the red, and we call that redshift. It means that we are receding from each other.
So I guess I'll draw a little bit here. So this is their assumption. This is what it means is because they've drawn a conclusion. Now I'd say maybe the conclusion is premature because the key is this photon, the photons, have traveled a great, long, huge distance to get here. And in that travel, they may have encountered something that causes them to have their frequency altered. They've passed through common barriers and maybe in common proportions when you think about the length of time. So if you had a sun, oops, you'd have to turn the drawing on. Start drawing without the drawing on, it won't draw right. And then this video will be not as useful. It's close enough. Not exactly centered, but it'll do. Alright, so this is a little bit awkward. Haven't got it exactly correct today. One of those days. It doesn't matter. Alright, so you have a source. And little tiny light rays, I mean they're very short, are traveling to us this terribly horrible, awful distance away. Now, each one of these rays could, at any one time, pass through a little molecule of something, and because there's lots of little transparent molecules, hydrogens and oxygens and all kinds of stuff, and especially if there's a bunch of gas in this cluster of galaxies or some other crap that this thing is actually in, these little photons have to travel through that medium, just like the light here is traveling through the atmosphere, the transparent, it's hitting a bunch of atoms. It doesn't hit the atmosphere, it hits individual atoms, and the individual atoms, it goes right through them, transmits through them because they're transparent, goes in one side, comes out the other side intact. Now the trick would be, is this light's moving very fast, speed of c, so as it's traveling, it's less likely to get hit by little bits moving this way than little bits moving this way. Okay, I mean, just logically you can kind of understand these bits can't catch up to it because it's moving the speed of light, and so they're going to hit a lot more bits going this way than going this way, a lot more. And so if these little bits of light have to pass through a little atom and be transmitted, and the atom happens to be traveling this way, then the transmission from as it goes into the atom and then is transmitted, it will be as if it's being transmitted from something moving away from us. That would be the logic here. So even if this thing was stationary, this little thing isn't the thing it's hitting. And so the movement of that little thing, okay, is going to add a little tiny redshift. Might be a lot of redshift, who knows? Depends on how fast those little atoms can be moving. And the point is, again, is they're all going to be moving this way. Somewhere between 0 and whatever, 80% of the speed of light, who knows how fast they could be going. They're atoms, so I wouldn't suspect they're going that fast. But anyway, and so the idea would be over billions, okay, of light years even. Well, billions of light years. I mean, just an amazing amount of stuff. you know, a billion light years, just even thinking about it, or a million light years. You know, the distance light travels in a year, huge, insane amount of time, distance. So anyway, the probability ends up being very likely that even though these are all individual rays, proportionally, okay, they're like flipping a coin, and this is like they got heads this time, and the other guy gets heads, and the other guy gets tails, and this guy gets heads, and the odds are that every single ray is likely by the time it gets here have hit just about the same amount of junk and stuff going just about the same amount of speed. And so over this whole long distance, the odds are it's hit a lot of transparent molecules moving towards it, which means away from the target, and that's acquired redshift through that process. So the further away it is, this is perfectly consistent with Hubble's law. I mean, they call it a law. I mean, a law. Okay, the further away you are, the more redshifted you are. Well, it would make sense because you've had to travel through more of these little moving atoms that you've had to go through. And that would explain redshift without any necessity for this thing to be moving or this thing to be moving. Neither one of us have to be moving, and redshift is perfectly explainable. So, again, like I said, they draw a conclusion. They write off the subject. They don't do any further thinking about possibilities, other possibilities. And then they make whole theories about how the universe had to have an instantaneous millisecond huge expansion and had to be this and had to be that, because they made an assumption a little bit too prematurely. They prematurely ejaculated their premise and broke their understanding by not being a little more cautious in terms of drawing a conclusion. A little preachy, but it is the truth. I'm just saying it's a completely plausible explanation for redshift, and it disengages a whole bunch of physics now that's not necessary. Dark matter, dark energy, expansion, all kinds of stuff can just be thrown away, and we don't have to worry about it anymore. A bunch of woo.
If, however, I measure lambda prime to be smaller than lambda, so lambda prime smaller than lambda, we call that blue shift in astronomy, and it means that we are approaching each other. So we make reference to the direction in the spectrum where the lines are moving. I can give you a simple example. I looked up for the star Delta Leporis what the red...
So an interesting thing would be is that some of the stuff that is blue shifted is often stuff that has exploded, or it's very active. And so the scenario would be a little different, right? Because the light would actually be hitting stuff moving away from it. So it explodes, and then there's still something very bright. You know, it explodes, but it doesn't blow the thing up. You know, there's still a sun, or suns, in the case of a galactic explosion. And the light is now going to travel through the smoke ring, so to speak, coming off of that. And the smoke ring is going to be going the same way as the light is going in this case. So it's going to add a little blue shift to that photon that travels through something going the same way as it. So anytime a photon travels through something moving, expanding out, an explosion, that photon will be blue shifted by the cloud that's moving away, that's moving in the same direction as the photon. So another explanation that doesn't require now for these celestial bodies to be moving at insane speeds. See, the blue shifted things are moving half the speed of light. They calculate stuff like that. Big objects, they're not likely going that fast. So again, another reason to take a deeper look.
Shift is. There is a line that most stars show in their spectrum, which is due to calcium. Even has a particular name. I think it's called the calcium K line, but that's not so important, the name. In our own laboratory, lambda known to a high degree of accuracy, is 3933.664 angstroms. We look at the star and we recognize without a doubt that that's due to calcium in the atmosphere of the star, and we find that lambda prime is 1.298 angstroms higher than lambda. So lambda prime is larger than lambda. So there's redshift, and so we are receding from each other. I go to that equation, I substitute lambda prime and lambda in there, and I find that beta equals plus 3.3 times 10 to the minus 4. The plus for beta indeed confirms that we are receding, that our relative velocity is away from each other. And I find therefore that the radial velocity, I stretch it as the radial component of our velocity, is then beta times c, and that turns out to be approximately 99 kilometers per second. So I have measured now the relative velocity, radial velocity between.
It's really annoying.
Let's go, Lee!
Yeah, it's brilliant.
Between the star and me, and the question whether the star is moving away from me or I move away from the star is an irrelevant question. It's always a relative velocity that matters. How can I?
So again, it does matter, and especially in this circumstance, as stated, if the red shift or the blue shift is just being created by the path the photons have to take and their probability of interacting with matter on their way, then obviously the relative motion isn't a real motion.
Measure the wavelength shifts so accurately that we can see the difference of 1.3 angstroms out of 4,000. The way that it's done is that you observe the starlight and you make a spectrum, and at the same time you make a spectrum of light sources in the laboratory with well-known and well-calibrated wavelengths. Suppose there was neon in the atmosphere of a star, then you could compare the neon light the way we looked at it last lecture. You could compare it with the wavelength that you see from the star, and you can see very, very small shifts. You make a relative measurement. So you need spectrometers with very high spectral resolution.
Meaning that it has to be able to tell the difference between light that's whatever 640 nanometers and light that's 642 nanometers. Because the little line is basically going to be a color, a frequency.
So there was a big industry in the early 20th century to measure these relative velocities of stars, and their speeds were typically 100, 200 kilometers per second, not unlike the star that I just calculated for you. Some of those stars, relative to us, are approaching, other stars are receding in our galaxy. But it was Slipher in the 1920s who observed the redshift of some nebulae which were believed at the time to be in our own galaxy, and he found that they were at a very high velocity of up to 1,500 kilometers per second, and they were always moving away from us. And it was found shortly after that that these nebulae were not in our own galaxy, but that they were galaxies in their own right. So they were collections of about 100 billion stars, just like our own galaxy.
So again, they have galaxies moving, insanely fast, which just doesn't make much sense.
So when you take a spectrum of those galaxies, then of course you get the average of millions and millions of stars, but that still would allow you then to calculate the redshift.
The argument is look, all this stuff is momentum in the end. Motion is momentum. And it's one thing for a star to be, swirling around in a galaxy, and it's one thing for the moon to be swirling around the Earth and then swirling around the sun and all that stuff. But when you move an entire galaxy, that's all momentum. And when you move it really fast, that's a lot of momentum. So where did all the energy come from to do that? What pushed it? What accelerated it? Because its velocity has to be a byproduct of something that accelerated it. And then they just come up, that's when they have to come up with some kind of invention, where you just end up with some notion that there was this singularity, this little thing, and it blew up in some sort of way. It banged, but it doesn't really mean bang. And then all of a sudden, at one moment, it expanded 1,000,000 times or 1 billion times in one, spontaneously and instantaneously, it achieved this huge velocity. And that's where they've created all this energy. But it isn't out of anything real. There's no mechanism that gave all these things velocity. No ordinary mechanism that we understand. That people like me can understand. I can't even understand this idea of something having velocity without any, like the space shuttle, without any evidence of the force that causes it.
The average redshift of the galaxy, and therefore its velocity. And Hubble, famous astronomer after which the Hubble Space Telescope is named, and Hugh Mason made a very courageous attempt to measure also the distance to these galaxies. They knew the velocities, that was easy because they knew the redshifts.
So again, just a conclusion. Now Hubble collected a lot of this data for this redshift argument. That's why they call it the Hubble law. But I don't think Hubble was ready to draw conclusions. So it's kind of ironic that they, it's like what they've done with Einstein. They say Einstein predicted gravity waves, or had something useful to say on the subject when he really didn't.
The distance determinations in astronomy is a can of worms, and I will spare you the details about the distance determinations. But Hubble made a spectacular discovery. He found a linear relation between the velocity and the distances. And we know this as Hubble's law. And Hubble's law is that the velocity is a constant which is now named after Hubble, capital H, times d.
And they keep changing that H number, semi-dramatically. And so he's just saying that there's a certain amount of this speed is acquired per distance. So perfectly consistent with the more distance, the more stuff you hit, the more your H number will go up, the amount of shift. So perfectly sensible if you understand that the more distance the light travels, the more likely it has hit things moving in the opposite direction and therefore been shifted.
And the modern value for H, is 72 kilometers per second per megaparsec.
All right, so I think that number was as low as 40, so it's almost doubled.
What is a megaparsec? A megaparsec is a distance. In astronomy, we don't deal with inches, we don't deal with kilometers. That is just not big enough. We deal with parsecs and megaparsecs. And 1 megaparsec is 3.26 times 10 to the 6 light years.
All right, so that's 1 million light years. 3 million light years. This is just making it a little difficult to do the addition. So it's 70 kilometers per second. So something that would be 1 billion, then you're up to 250 whatever kilometers a second, and something like that. Yeah, so you could have made this simple, this math. Instead, they make it look more complicated than it needs to be.
And if you want that in kilometers, not a reasonable question, it's about 3.1 times 10 to the 19 kilometers.
I didn't want in kilometers.
So I could calculate for a specific galaxy that I have in mind. I can calculate.
It would have been nice if you just put it in light years without the -6 stuff. So I have to think about, okay, that's 6 zeros, so that's 1 million, right? Yeah, 6 zeros, 1 million, I think. Well, it's 10 times the 6, so it's 10 million.
Distance, if I know the redshift. I have a particular galaxy in mind for which the lambda prime.
So this is kind of a funny part too, because now they're using the redshift to tell them how far away something is, and there's obviously this proportional relationship, so you can get away with that, but they don't understand why there's a proportional relationship.
For which lambda prime is 1.0033 times lambda. So notice again that the wavelength that I receive is indeed longer than lambda, so there is a redshift. I go to my Doppler shift equation, which is this one. I calculate beta, one equation with one unknown, can solve for beta, and I find now that v is 5,000 kilometers per second. Very straightforward, nothing special. Very easy calculation. But now with Hubble's law, I can calculate what d is, because d now is the velocity, which is 5,000 kilometers per second, divided by that 72, and that then is approximately 69 megaparsec. Again, we have the distance, if we do it in these units, in megaparsec. That's about 225 million light years. And so the object is about 225 million light years away from us. So it took the light 225 million years to reach us. So when you see light from this object, you're looking back in time.
Yes, but looking back to when the dinosaurs roamed the Earth, right? So, that's how long a trip it was. And just think how realistic is it that those photons never hit anything in that whole long travel.
And if you have a galaxy which is twice as far away as this one, then the velocity would be twice as high.
I mean, the vacuum of space really isn't a vacuum. There is stuff floating around out there.
And they're always receding relative to us. I'd like to show you now.
Except the stuff that's blue shifted. So they're always receding except for the exceptions.
Some spectra of 3 galaxies. Can I have the first slide, John? All right, you see here a galaxy. And here you see the spectrum of that galaxy. That may not be very impressive to you. The lines that have been recognized to be due to calcium K and calcium 8 are these 2 dark lines. Some of you may not even be able to see them. And this is the comparison spectra taken in the laboratory.
So those are absorption lines. So they're looking at what light doesn't come off of an object, meaning it was absorbed by the object.
These lines are seen as dark lines, not as bright lines. We call them absorption lines. They are formed in the atmosphere of the star. Why they show up as dark lines and not as bright lines is not important now. I don't want to go into that. That's too much astronomy. But they are lines, and that's what counts. And these lines are shifted towards the red part of the spectrum by a teeny weeny little bit. You see here this little arrow. And the conclusion then is that in this case, the velocity of that galaxy is 720 miles per second, which translates into 1150 kilometers per second. And so that brings this object, if you believe the moderate value for Hubble constant, at about 16 megaparsec. This galaxy is substantially farther away. No surprise that it therefore also looks smaller in size. And notice that here the lines have shifted. These lines have shifted substantially.
So I would argue that the prediction of distance is probably more accurate than the prediction of velocity. That would be one thing I could say. Obviously the prediction of velocity is garbage, if I'm right. But the prediction of a proportional distance is probably okay. But again, that's they're fudging this Hubble constant because it's all based on a reference. So they first have to figure out how far away one thing is before they can figure out how far everything else is based on this redshift theory. So it is sort of that's the messy part, is they have to go based on how bright something is and how sure they are about how big it is. And those are not things the photographs tell them.
Should live further. And if I did my homework, using the velocity that they claim, which they can do with high degree of accuracy, because you can calculate lambda prime divided by lambda, those measurements can be made with enormous accuracy. Enorm
accuracy. No, I'm afraid not. They can be made erroneously and wrong very easily.
I find that this object is about 305 megaparsecs away from us, so it's about 20 times further away than this object. So the speed is also about 20 times higher, of course, because it's a linear relationship. And if you look at this one, which is even further away, then notice that these lines have shifted even more. The next slide shows you.
So again, their argument is that the things closer to us are moving away from us slower than the things further away from us. So another break in continuity, in the sense that that sort of means the Earth is in the middle of the universe thing again. You're stuck with a Earth-centric view of the universe. So another reason to doubt that this is a correct way to look at it. Why would the things further away from us be moving faster, and the things closer to us be moving slower? Why? Yeah, that doesn't fit.
What I would call Hubble diagram. It was kindly sent to me by Wendy Friedman and her co-workers. Wendy is the leader of a large team of scientists who are making observations with the Hubble Space Telescope. You see here distance, and you see here velocity in the units that we use in class, kilometers per second. Forget this part, that's not so important. But you see the incredible linear relationship. And Wendy concluded that Hubble's constant is around 72. It could be a little lower, it could be a little higher. She goes out all the way to 400 megaparsecs with associated velocities of about 26,000 kilometers per second. That's about 9% of the speed of light.
So again, a huge speed for very large objects. And just conveniently, right? Those things with huge speeds, fortunately, are not anywhere near us. Isn't that convenient, right? So, again, lots of reasons to doubt that this is the right way to understand what the mechanism is. Just it's too... It just smells of an unlikelihood, again, that we are in the center of the universe.
So beta is about 1/10. So for this object, lambda prime divided by lambda would be about 1.1. There's a 10% shift in the wavelength. Hubble, who published this data in the 20s, his whole data set, when he concluded that there was a linear relation, had only objects with velocities less than 1100 kilometers per second. And 1100 kilometers per second is this point here. So Hubble had only points, there's not even any in Wendy's diagram, which are here. And he concluded courageously that there was this linear relationship. And you see it has stood the acid test. We still believe it is linear. The only difference was that Hubble's distances were very different from what we believe today. They were about 7 times smaller. So Hubble caught.
So 7 times smaller, so the number has changed by a 7-fold.
Constant was different for him, but the linear relationship was there.
So I guess his Hubble constant was 1. That makes sense, right? He started off with the number 1, and now it's up to the number 7, 70.
Okay, that's enough for this slide. So now comes a $60 question. Why do all galaxies which are far away, why do they move away from us? Well, I can suggest a very simple picture to you. We are at the center of the universe, and there was a huge explosion a long time ago. We refer to that explosion as the Big Bang. And since we are at the center where the explosion occurred, the galaxies which obtained the largest speed in the explosion are now the farthest away from us. Now assume that this explosion is the correct idea.
So again, it would be the only way you could have a Big Bang. So what they're going to try to suggest is that every single bit in the universe is leaving every other bit in the universe, and that somehow that means, okay, that the stuff further away from us is leaving us quicker, which still doesn't make much sense. You can't. I think he's going to blow up a balloon here, to illustrate it, but even that wouldn't make sense because that's a curved surface and you wouldn't be moving further away. The further away you got. So, I mean, I'm just saying, is that what they're going to suggest the Big Bang was? Is that, I don't even know how to illustrate that. Because clearly the universe has a thickness it's spherical. It looks as big this way as that way as that way as that way. And if we were on the surface of something, we'd be able to see how thin the surface is.
Assume that there was a Big Bang, then I can ask the question, now when did it occur? I can now turn the clock back And I can do the following. I can take two objects which are a distance d apart today, but they were together when the universe was born at the Big Bang. And let's assume that they have been going away from each other always with the same velocity. Let's assume that now for simplicity. If they always went away with the same velocity from each other, then the distance that they are now today is their velocity times the time t, which is then the age of the universe. But we also know.
Another, you sit there and try to imagine what he's talking about here, and it really doesn't make any sense, because we know that there's a lot of objects in the universe that are very close together and objects that are very far apart, and they all had to be in the same place at one time, and it just doesn't make sense that they are in such different places now.
It's Hubble's law that the velocity v is h times d, and we assume that these velocities.
Another commercial.
Let's go, man!
I'd almost say that that is racist. I mean, what is that? Oh.
These velocities are the same now for simplicity. You multiply these two equations with each other, and you find immediately that the age of the universe is 1 over h. And that indeed has the unit of time. If you take h, the one that we believe in nowadays, and you calculate 1 over h, and you work in MPS units, you'll find that th is about 14 billion years. I'll first give it to you in seconds. It's about 4.3 times 10 to the 17 seconds. And that is about 14 billion years.
Just conveniently about the end of the distance that the Hubble telescope can see. So it just happens to be kind of convenient.
So with this picture in mind, the universe would be about 14 billion years old, but because of the gravitational attraction of these galaxies, they attract each other, you may expect...
Says him. I mean, they might attract each other, but it's such a... Compared to their velocities, their amount of attraction would be insanely, insipidly meaningless. I mean, if they're going 20% the speed of light, their attraction to each other is going to be just the tiniest of a deflection.
That the speed of the galaxies was larger in the past, and therefore the speed that we assume that the speed doesn't change is not quite accurate, and so maybe the universe is a little younger, maybe 12 billion years or so. We know from theoretical calculations that the oldest stars in our own galaxy are about 10 billion years old. Therefore, the universe cannot be younger than 10 billion years. And there's general consensus in the community that our universe is probably 12 to 14 billion years old.
Yeah, well, just consensus based on assumptions, so blah, 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 blah. I don't know exactly how they tell how old the stars are in our own galaxy, but whatever to that one. I'll just say whatever to that one.
Now, the whole issue of this deceleration that I mentioned, as the galaxies moved away from each other, is at the heart of research in cosmology. And in fact, it is now believed that very early on in the universe there was first acceleration, followed by deceleration, and maybe again acceleration. That is quite mysterious.
It's just silly. Magical accelerations from no cause, then stops, and then accelerates. And it just doesn't make any sense. It can't be the right answer. You're, sniffing in the wrong whatever place to be sniffing.
Frontier research is going on in this area. At MIT we have 3 world experts. Professors Alan Guth have made major contributions to this concept, cosmology. We have Max Tegmark, and we have Scott Hughes. So now comes a reasonable question: how far have we been able to see into the universe? And to my knowledge, this year, which means in 2002, the record holder is a galaxy for which lambda prime over lambda is 7.56. Was published only 2 months ago. 7.56. Now, at such very large values of redshift, general relativity becomes very important. And the equation that we derived here was derived with special relativity. So with very high values of redshift, like lambda prime over lambda 7.56, you cannot reliably calculate the velocities using that equation. And so you cannot use that velocity then and shove it into Hubble's law and find the distance.
Yeah, you have to put a gamma on it. Blah, 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 blah. Horse shit.
But there is no question that that object emitted the light that we see now about 13 billion years ago. It's very...
No question. You know, it's really not that kind of evidence. The no question kind of evidence. It's just not that good.
Very far away from us. I will show you an object. It comes up in the next slide.
The light that we see now was emitted about 12 billion years ago.
So for one, when you look at that object, there it is. It doesn't look very impressive.
But what do you expect from an object so far away?
It's a quasar, which is a very peculiar...
So they say they know what it is, and they say all this stuff, and you can see from the image it's square. I mean, it's so pixelated. Yeah. Oh yeah, but we know what it is. Sure, no problem.
Galaxy. It emits emission lines. The spectra do not show these dark lines that I showed you earlier, but they actually have emission lines. And the light that you see here was emitted some 12 billion years ago.
Not really seeing anything, frankly.
And now comes the spectrum from this object in the next slide. This was published last year by Scott Anderson and his co-workers, University of Washington in Seattle. I have collaborated with Scott on many projects. So here you see the spectrum of that quasar that you just saw. And here you see a line, an emission line, at roughly 7,800 angstroms. And there are all reasons to believe that this, in the frame of reference of that quasar, was the Lyman alpha line, which is emitted by hydrogen, which is 1,216 angstroms. Now we have here 5,000, 4,000, 3,000, 2,000, 1,000. So here is roughly where the wavelength lambda is, and here is lambda prime. Lambda prime is 6.41 times larger than lambda. He mentions 5.41, but Z is what astronomers in general quote, is lambda prime divided by lambda minus 1. So the ratio of lambda
So they're going to give it a preposterous speed.
prime over lambda is 6.41. Absolutely amazing that you can make such accurate measurements, such incredible, beautiful data.
So they say it's beautiful data, incredible, all this stuff, but we really don't see how any of this data was manufactured. I mean, these are obviously very long time exposures to get this information. Who knows?
And this line is all the way in the infrared. You cannot see this with your naked eye anymore.
You can see up to about 7,000 angstroms.
So the 1216 line was in the UV, shifts all the way into the infrared, and this allows astronomers then to measure the value lambda prime over lambda.
Galaxies that we see now, those that emitted their light about 12 to 13 billion years ago, are now at a distance from us which is about twice as far away as 12 to 13 billion light years. Thus, they are at about 25 billion light years away.
Right, so this idea that the universe has grown that much, you know, comes with it all kinds of conundrums, and well, there's no point in saying things like this, but I mean, they sort of know that these quasars are immature galaxies, young galaxies, strong galaxies. And there's a sort of logic that would tell you that wherever that thing is now, it's a galaxy now. It's big. It's falling apart.
That's the result of the expansion of the universe. Yet the age of our universe is very close to 1 divided by the Hubble constant, which is about 14 billion years. I calculated that by assuming for simplicity that the expansion of the universe was constant in time. The reason why the 14 billion years is still quite accurate is an accident. It turns out that the acceleration and the deceleration of space approximately cancel each other out. The horizon of our universe...
Just the acceleration and deceleration of space. I mean, again, so I have to believe in the magical space accelerating. Nothing goes very fast, and then nothing stops. Oh, friggin'. What a pile of poo.
is at an even larger distance than 25 billion light years.
So this is all crappy added post-production.
It's about 45 billion light years. Beyond that distance, radiation hasn't had time to reach us. That's enough, John, thank you. I'd like to return to the Big Bang, to the explosion, some 12 or 15 billion years ago. And I'd like to raise the question, are we at the center of that explosion? Are we really at the center of our universe? That cannot be, of course. It's an incredible arrogance to be too egocentric. I know that we all think very highly of ourselves, but this cannot be. We are nothing in the framework of the total universe. We cannot possibly be at the center.
It's retarded to say we're nothing, but yes, it would be a hell of a coincidence.
So how do we reconcile this now with what we observe? Imagine that you were a raisin in a raisin bread. Quite a promotion from a human being to a raisin in a raisin bread. And I put you in an oven. And the raisin bread, the dough is going to expand. All raisins will see other raisins move away from each other. And the larger the distance to your raisins, the larger the speed will be.
Well, this really doesn't happen, and realistically, it's the bread is in a pan and only really expands in one direction, so it's kind of bullshit.
And each raisin will think that they are very special. Suppose here, this is you, one raisin, and here's another raisin, and here's another raisin. After a certain amount of time, all distances have doubled, so this one is here, and this one is here. So you can immediately see that when you look at this one, that its velocity is substantially lower than this one. Is it twice as far away, you will see twice as high a speed. But this raisin will look at this one, and it will also conclude that this raisin, relative to this one, has a higher velocity than this raisin.
Right, and if this distance was increasing, then the light would take longer to get where it's going. So then your predictions of distance are wrong because the light is traveling all that extra distance that you just made up. Pretty much. Well, I mean, it's really not traveling any extra distance, you know, because we don't live long enough to see the differences. What else would be a factor there? Well, anyway.
That's relative to this one. So all of them will think that they are special, and you as a raisin would come up with Hubble's law. You would conclude that the velocity of your other raisins are linearly proportional to the distance.
Right, but you were supposed to start in the same place. So then again, you're already in trouble. So you're saying it's relative to your distances. So you're saying everything was in a relative position, and then you expanded everything. So who does that make sense to? I mean, that's better than the Earth's in the center thing. So the idea that you start off with everything in a proportional, a little tiny verse, a smaller verse, and then the smaller verse just happened to go boing, boing, and it's still now it's the bigger verse, and everything's in the same relative position. Does that make any sense to anybody? Doesn't make any sense to me.
There's an analogy which is even nicer than raisin bread, and that analogy is with flatlanders. A flatlander is someone who lives on a two-dimensional world.
Right, which again, it's not a good analogy, is it? Because we don't live in a two-dimensional world. We live in a three-dimensional universe. So why do we keep using these two-dimensional bent space analogies and analogies that are completely corrupt because they really don't fit in the real universe, which has three dimensions?
He happens to live on the surface of a balloon. And light travels only along the surface of the balloon. So the two-dimensional world is curved in the third dimension, but the flatlanders cannot see in the third dimension. They can only see the second dimension. So here you have such a...
Yeah, so obviously they can't see. They can't see around a curve, so it's not going to do them much good, is it? No.
The world. So here are the galaxies. Flat world, and the universe is curved in the third dimension, which these flatlanders cannot see. And when you blow this balloon up. The galaxies move away from each other, and the farther the galaxies are away from each other, the higher the velocity.
Which just means their velocity is increasing because of the sphere he created. Spheres don't linearly expand, they expand at, the pi. They get bigger than the straight line by that 3.14 thing. So the surface is expanding, which means the distances are longer because it's a sphere. It's not straight lines. But there's no evidence the universe is that.
This model works actually quite well, and I want to pursue that in my next calculation. Let me first try to bring this universe to a halt, because I don't want the universe to collapse again. Okay, I succeeded.
Very exciting.
So you can pursue this idea very nicely, and you can see that the flatlanders would draw quite amazing conclusions.
Again, it's...
Here is that balloon. The balloon has a radius r. Here is one galaxy, and here is another galaxy. And they are a distance s.
There is no flatlander. Obviously, it's a curved surface, so it's not a flat universe, and so blah, blah, blah. None of this, drivel is very explicitly metaphorical.
Part. I will call that later D, but now I want to call it S. You will see why. A little later in time, the universe has expanded. This galaxy is here, and this galaxy is here. And this distance now is r plus dr, and so this distance now between the two galaxies is s plus ds. And it follows immediately from the geometry that s plus ds divided by s is r.
Oh, another
Booking.com.
fun
We
commercial.
can't guarantee you'll find gold on your Wild West vacation, but we can guarantee the best price on that there rental cabin, or any hotel, home, boat.
Is r plus dr.
Kind of funny that physics professors, even in retirement, they got to collect the whatever, a few petty dollars.
Divided by r. Simple high school geometry. I can work this out. I get SR plus RDS is SR plus SDR. I lose this SR. I divide by dt. ds dt is the velocity with which these two galaxies move away from each other. That's what they would measure in their universe. So there's a v here. It's clear that s is the distance between them. I will call that d again now. So that is d. And then I have 1 over r times...
All right, so just to understand this is almost like that laser beam kind of thing where you could say I could move a laser beam from Mars to the moon, in milliseconds, and I violated the speed of light because the light moved. It didn't really move. It's not a real velocity. So again, this idea of expanding space doesn't mean the thing has actual velocity, actual momentum, actual anything. And but again, well, how could it not? Realistically, if the space keeps expanding and it crashes into something expanding the other way. But see that they have the catch where everything somehow is moving away from everything else. Like there's some sort of magical little thing in the space that's just making more space and pushing everything away from everything else. And this I'd say it's a very low probability this is the truth.
The rdt. 1 over r. I will write this a little higher. dr over r. No, we have the rdt. So now I have 1 over r dr dt. And look at this. I have v equals d times something. And that something, at a given moment in time, has a unique value. R of the balloon has a unique value, and the rdt, which is the expansion velocity, also has a unique value. And so it's immediately obvious that in this universe, this is Hubble's constant. And this Hubble's constant is a function of time. It is changing with time. And it's obvious that it should change in time. No reason why it shouldn't do the same in our own universe.
Right, it's expanding faster and slower and faster because God has to take a breath before he blows up the balloon some more. Shit.
Because r in the past was much smaller. So even if you take an expansion velocity, which is constant, if r is smaller in the past, then h was larger in the past. And that is the reason why if you ever see a quote of h to be 72 kilometers per second per megaparsec, there's always a little zero here. And the zero means now. The zero means not a billion years from now and not a billion years ago. We really don't know what it was a billion years ago. Now don't carry this analogy between the 2D balloon and our own universe too far, but it gives some interesting insight.
Yeah, you drew all that math and did all this crap because you're, oh yeah, well, I'm not really saying it. Yeah, you are.
It is suggestive of the idea that our own three-dimensional space may be curved in the fourth dimension.
The magical new dimension that I'm going to add to save the day. Great physics.
We cannot see. This is very fascinating, and I would advise you.
I know, it's just crap. It's just a bunch of made-up manipulations of concepts to try to keep your wrong assumptions viable. And that's all this mush is. Instead of just going back to your assumptions and saying maybe they're stupid assumptions, let's start over. You just keep trying to engineer a fix. You just keep saying it's broken, but we're just going to keep gluing new crap on it to make it functional. And functional just means fixing its gross errors.
If you are interested in this area, that you take a course in cosmology, you should also take one in general relativity. It will open a whole new world for you.
And Alan Goose, Scott Hughes, and Max Tegmark are the experts in this area. And they also happen to be very good teachers.
So, can't look
Says you.
there. Now comes the key question, and that is, will our universe expand forever? It's also possible that our universe will come to a halt. That means that h, Hubble's constant.
Yeah, well, you're just making up possibilities. It's also possible that rhinoceroses will figure out how to fly, and boy, will we be in trouble then.
Will become zero, that everything will stand still, no relative motion anymore, which then will be followed by collapse. And so all the redshifts will then come to zero and will turn to blue shifts. It's the same idea, same question. When you throw up an apple, will the apple come back?
It's hardly the same question. It's not even close to the same question. No reason. They're just, like I said, they're just making up this, well, somehow all of this expanding will stop, and then everything won't have any velocity from the expansion because it wasn't real velocity. It was just the space expanding, and the things never got any velocity from that pushing. It wasn't real pushing after all, so they don't have any velocity, so they don't have to lose their velocity. No force has to act on them to stop them from moving because they never were really moving. I mean, it's just stupid.
Will the apple not come back? It depends on the speed of the apple and on the gravitational field of the Earth, and we all know that if you throw it fast enough.
Yeah, we all know that you're not going to throw the apple off the Earth, and we know the rules of gravity, and they really don't have a damn thing to do with it expanding bullshit.
About 11 kilometers per second in the absence of atmosphere, the apple would never come back. Now, if only gravity played the key role in our universe, then we can do a very simple calculation.
The answer to the question whether our universe will expand forever or whether it will collapse would then only...
You need to 11 kilometers per second, so you have to throw it like 22 miles an hour or something to its escape velocity, something like that. I don't know. I wish he just would have put it in kilometers. How fast do I have to throw the apple to escape? That's what he should have said.
depend on the average density of the universe.
And when I say average density, then you have to think in terms of a big scale. You don't think in terms of Cambridge. That's not representative for the average density of the universe. Nor is our solar system. Nor is our galaxy. But you have to think probably on the scale of a few 100 million parsecs. Maybe 500 megaparsecs. And so I bring you out.
It doesn't matter because you've invented this phony dark matter that has all of this gravity in it. So, you know, there's no point in talking about what's in the universe because you've put most of the stuff in the universe as some sort of invisible fake shit.
Now into the universe. Here is the universe. And these are galaxies. And here is a sphere. It has a radius r. And that's on a scale of about 500 megaparsecs. So rho, average density, is representative for the universe. And here, let's suppose you were here, where I can take any part in the universe, there's nothing special about it. And you see here a galaxy, and that galaxy moves away from you with a velocity v. That galaxy has a mass little m. The mass inside here, capital M, inside this sphere, is 4/3 pi r cubed times rho. It's the average density, right? Now we know from Newton that the force that this galaxy will experience is only determined by the mass inside this sphere and not by the mass outside the sphere. And so if I want to calculate whether these two objects will forever move away from each other or whether they will fall back to each other, then all I have to make sure that I make the total energy 0, the sum of the kinetic energy and the potential energy must be 0. So 1/2 mv squared of this object must be mmg divided by r.
So, and it's basically just going to kill the velocity again. So they're moving away from each other, but they're not really moving because they have no momentum that has to be overcome.
That is when the total energy is 0. We will expand forever and ever and ever, and it will never come back. Little m cancels out. And capital M, I can write 4/3 pi r cubed rho. Here comes my g, and here comes r. Notice that the r cubed upstairs becomes r squared. And so if I have an r squared here and I have a v squared here, remember that v divided by r, that is Hubble's constant. Because r is d, it's the distance between us and the galaxy. And so v squared divided by r squared is the Hubble constant as we measure it today, squared. And so you'll find then, from this simple result, that rho, as it should be today, that's why I put a little 0 there, is 3 divided by 8 pi. I get a g there, and I get 80 squared. And so this tells me that if the density, the average density of our universe, is larger than this value, then our universe will come to a halt and will collapse. And we can calculate that value. Because we know 80, we think we know g. And so you will find then, I'll write it down here, that rho 0 is about 10 to the minus 26 kilograms per cubic meter. And so if rho is smaller than this amount, then we will continue to expand forever. If the mean density right now is larger than that amount, then expansion will come to a halt, redshift will become blue shift, and we will collapse again. The matter here, this matter density,
Doesn't have to be galaxies or gas or tomatoes or potatoes. It could be dark matter.
so don't think of it necessarily as this being just stars and galaxies and tomatoes.
Yeah, that's right. We can just make up anything we want to. So why would we bother with the formula when we're just going to make up how dense the universe is anyway? Fuck.
It is generally believed today that the expansion of our universe will not come to a halt and collapse. But our views could change. Enormous development has been going on in the last 10 years, and you can read about that in the New York Times. Almost every month you will read something about the enormous progress that's being made in cosmology.
BS.
And of course the idea of whether or not the universe will expand forever is something that's emotionally an important issue for us.
I don't know why. Why? Like, emotionally interesting.
If the universe will expand forever, and stars will all burn out, and the universe will become a cold, dead, and boring place.
On the other hand, if the expansion will come to a halt,
No more assholes. Oh dear, what a pity. No little poo robots. Oh, I'm so emotionally troubled by the thought of it. Maybe not.
the universe will collapse.
And it will end up with what we call the Big Crunch, as opposed to the Big Bang.
Well, both choices seem kind of suck then, don't they? It's supposed to be the big whimper versus the big collapse or crush. You can't have it both ways. Can't bang if it left.
And it will be hot, there will be fireworks. It will be like the early days of the Big Bang. Temperatures of billions of degrees. I'd like to read a poem from Robert Frost, which he wrote in 1920, called Fire and Ice.
La 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 physics.
Some say the world will end in fire, some say in ice. For what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice,
Yes, I want to have more torture. Torture's fun.
I think I know enough of hate to know that for destruction, ice is also great and would suffice.
There are many people who want our universe to come to a halt. And
Yes, I'd rather just this planet. Swish. There, problem solved.
collapse.
Probably for emotional reasons, maybe for religious reasons, maybe it's more aesthetic, maybe it's more reassuring, maybe it's more romantic. I don't know.
But if that is not the case, then the end is not very spectacular.
Well, again, the end. It's going to be the end. So you're basically saying, how do I want to die? Freezing to death or boiling to death? I take freezing.
T.S. Eliot wrote, "This is the way the world ends, not with a bang, but a whimper." Now it is conceivable that the expansion of the universe will come to a halt, and that the universe will ultimately collapse. We will have a big crunch, and it is even conceivable that a new universe will then be born afterwards, that there will be a new Big Bang. And if the evolution of that universe
Yes, we can all do this. I can imagine rhinoceroses with nice little fluffy wings flying around, horning people. Yes, I can imagine it. Not much chance of it, though.
were a carbon copy, exact carbon copy of the present universe, a few thousand billion years from now, we may have a great 802 reunion. Same place, same time, same people. Perhaps see you then.
Brilliant. Thankfully, we are concluded at this portion of our broadcast day. And, it's just made up. It's just made up. So they get enough people together to make up a bunch of crap, construct some little formulas, lambdas and doodars and this, that, and the other thing, and they and there. We're all going to live in little gingerbread houses in, Witch County. Just such crap. So anyway, I guess I should play the last few seconds. Just to be fair. Yeah, not much of an applause for that one. Yeah, good. Oh, I didn't have it turned on. Well, you didn't miss anything. Well, except the balloon expanding, all the other crap, but doesn't matter. I mean, sorry, that was my failure. I should have checked. It would have been the right thing to do. I'm new to this too. Okay, it's not like I went to making video school. So anyway, sorry. I'll apologize. I'm sorry. Shouldn't make mistakes like that. Anyway, till the next time and such.